Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera and good day. This is BMM 1533 Strength of Materials 1 and I'm Dr. Siti Rabiatul Aisyah binti Idris will be your lecturer for today's lecture. So for today we are going to continue with our topic which is in CO3 chapter 3 with pure bending. Well, basically this is the last part of topic 3 CO3. So first of all, let's look at the chapter objective, which is for today we are going to learn on how to analyze the stresses and strains problem in members subjected to pure bending and transverse loading. Meanwhile, for the lesson objective for this subject is stated such as follows, and you may read it on your own. Okay, so let's look at the bending analysis and design of beams for bending. Well, I think you have seen this example in our previous lecture. So basically in this topic we are going to look at on the failure of this structure which is subjected to pure bending. Okay, in this topic, in this lecture, for today's lecture, we are going to look at on types of beams. After that, we are going to look at on shear force and moment diagram using singularity functions as well as using integration. After that, we are going to look at other types of example or applications involving bending load. Types of beam, there are three types of beam which can be found nowadays. Simply supported beam, if you look at the diagram here, so this one is pin support and this one is simply supported. After that, cantilever beam. Number 3 is overhanging beam. As you look at this one, this is the area of the overhanging beam. So there are three types of beams that can be found. Loads on the beam. Well, before this we have learned that there are several types of loading, which is shear force. Yeah, so this is shear force with 15 kilonewton, and the other one is moment itself, this one, which equals to 80 kilonewton meter. And there's another one, another types of loads which could exist on the beam, this one, uniformly distributed load they call it, and the value, if you look at here, equals to 5 kilonewton per meter. And therefore, if we want to calculate the value of forces here, then we need to multiply with the total length of that load being applied on the beam. So if you look at here, 5 kilonewton per meter will be multiplied with 5 meter length. And this one can be the location of the load itself will be at the center of that length, which means 5 divided by 2.5 meter length. Now, this is the shear force and bending moment sign convection. Alright, if you cut the section, okay, again in this topic, we are still going to use cutting section. Same goes to our previous lecture. So if you cut from this point until to this point, the value of the sign convection for internal shear is downward, whereas and for moment it will move counterclockwise. And if we cut from this point until this point, from right to the left, the sign convection for shear, internal shear is upward, and for moment is clockwise direction. So this sign convention need to be remembered, otherwise you are going to draw wrong shear force and bending moment diagram. Okay, so now let's look at the shear force and moment diagram using singularity function. Okay, straight away to example. So this is simply supported beam, and the value of force here is P at the center of the beam. The question asks you to determine the variation of internal shear force and bending moment along the beam. So the first step that we need to do is draw the free body diagram and find the value of reaction forces at both ends, right and left, left and right. So from free body diagram, we know that the area of reaction force here is P over 2, and this side also P over 2. So after that, we start to cut the section, which is for this case, I would prefer to cut from left to the right. So draw a free body diagram after you cut the section. Some students ask, when can you stop the cutting section? So actually starting from this point, and then you need to start before the additional reaction force axis, in this case somewhere here. So from there, draw a free body diagram for that section that have been cut. And here you may see this is the sign convention for reaction force for internal shear V, and a moment which is counterclockwise. After that, from here we need to find the value of V and also M. So taking total forces in y direction equals to 0, you'll get V equals to P over 2. Whereas for moment, taking a moment at X point, which is somewhere here, X point, equals to 0, so M equals to P over 2X. Alright. Now, continue our cutting section, which is from here, moving forward after value of P here. Then draw the free body diagram. You see the sign convention for internal shear force and moment is still the same, because the cutting direction is still from left to the right. So the same steps, you need to find the reaction forces in y direction, as well as taking a moment at X point there. So taking a total forces in y direction equals to 0, then you'll get V equals to negative P over 2. After that, for moment at point X equals to 0, you'll get M equals to P over 2 times L minus X. From there, so basically this is the so from this equation, this formula for this equation, we can find the coordinate actually, because whenever we want to draw a graph, we need to know its coordinates. So by right, for shear force, this is the coordinate, which is when X equals to 0, V equals to negative P over 2, and when X equals to L, V equals to negative when X equals to L, V equals to negative P over 2. And for this case, when L equals to 0, X equals to 0, M equals to PL over 2, and when X equals to L, then M equals to 0, and when X equals to L over 2, right, then it will be PL over 4. So this is the graph. This is how you draw the graph. All right. So each point here actually referring to your own calculation. All right. Let me repeat. Okay. So this is the axis Vx. So this is shear force diagram. At this point, X equals to 0. What is the value for P? So refer it back to your equation, the first section that you have cut. V equals to P over 2. Alright, so V equals to P over 2 until this point, which is L over 2, the distance itself. Now, from this point until that point, what would be the value of shear force here? So, you refer it back, the section that you have cut here. And then from here, you'll get V equals to negative P over 2. So, go back to your diagram, negative P over 2 until this point. Alright, now move on to moment. So moment here, you have the value of x there, which means this one is same as y equals to mx plus c, which is linear graph. So you need to include the value of x in there. So when x equals to 0, you'll get the value. Is it true? No. When x equals to L, so m will be equal to no, I think this one is another section. Oh, this one. Okay, the first point, sorry, my mistake, yeah. For the first point here, refer it to the first cutting section. So here m equals to px over 2. So when x equals to 0, you'll get m equals to 0. So mark the point 0 here. Now move on to next section, which is when x equals to L over 2, you'll get m PL over 4. So mark PL over 4 there. After that, for the next point, you need to refer to this diagram, which is here. So when x equals to L, you'll get m equals to 0. So mark this point there. So you get this graph for moment diagram. See? Alright. So to get a better understanding, so now let's move on to example number 1. Question asks you to draw a shear force and bending moment diagram by looking at this diagram. So this is simply supported beam with bending moment reacting on that beam at the center. So the first step is that, as usual, we need to draw free body diagram and then find the reaction forces at pin A and also point C. From there, we'll get the value, which is equals to m naught over L. Same goes to point C. After that, you need to start to cut the section, alright, from left to the right. Stop before point B here. So draw a free body diagram for that section. Notice the sign convention here. So you need to remember sign convention for shear force is moving downward, whereas for moment is counterclockwise. From there, you need to calculate total forces in y direction equals to 0. So you'll get V equals to negative m naught over L. So 0.1. And for moment, taking moment at point X equals to 0, you'll get moment equals to negative m naught over Lx. So point coordinate for moment is that when x equals to 0, m is 0. The other one is when x equals to L over 2, m equals to m naught x equals to m naught over 4. Actually, this is a mistake, yeah. M naught over 4. M naught over 2. Yeah, this is correct. Okay. So continue to cut the section. Alright. So draw again its free body diagram. After that, taking a total forces in y direction equals to 0, we'll get V naught equals to negative m naught over L. And for the moment, you'll get m equals to m naught minus m naught over Lx. From there, when x equal, by taking the Lx equals to L over 2, you'll get m equals to m naught over 2. And when x equals to L, you'll get the value of m naught equals to 0. So by right, you have all the coordinates, which can be used to draw shear force and bending moment diagram. Alright, so this is V axis and X axis for shear force, and this one axis for bending moment, and this one is X axis. So when X equals to 0, V equals to negative m naught over L, and when X equals to X, it is the same, and V equals to negative m naught over L. Whereas for moment, when X equals to 0, m naught equals to 0, and when when X equals to L over 2, firstly, m will be equals to, if you refer to this equation, when X equals to L over 2, m equals to negative m naught over 2. After that, by referring to our calculation coordinate here, when X equals to L over 2, you'll get m naught over 2, and when X equals to L, then you get another value of m naught, which is equals to 0 here. So by right, total moment at this in the beam for that line need to equals to 0. So you must be closing the graph itself. Otherwise, the bending moment that suffers by the beam itself is not stable. Okay, now let's move on to example number 2. This one by taking a different types of a loading, which is uniformly distributed load. So how can we solve these types of problem? Okay, first of all, as usual, we need to draw a free body diagram. But this one, okay. Alright, before that, it either can be done by draw a free body diagram for the total total length itself, or we can just straight away cut the section. For this case, cut the section from point A to somewhere before point end point L there. So if you notice here, the dot line here, this one actually represent uniformly distributed load. However, for this case, when we draw free body diagram, we need to take an average of that uniformly distributed load by taking a length that have been cut. For example, for this case, if you cut from point A until X value there, so the average value for a uniformly distributed load is W times with X, and the force will stand in the middle of X, which means X minus 2. From there, you need to find the value for shear force and also moment. So you'll get V equals to W times L over 2 minus X. Alright. If you notice here, there's a value of X here, so you need to include the value of X in order to draw the diagram. For example, when X equals to 0, from this point, you'll get V equals to WL over 2. And when X equals to L over 2, you'll get V equals to 0. And when X equals to L, you'll get V equals to negative WL over 2. After that, the same step, taking a moment at point X equals to 0, you'll get this equation. After that, substitute the value of X's from 0, L over 2, and L. So by right, you'll get all the coordinates that you need in order to draw shear force and bending moment diagram. Okay, so just substitute in here. Using all the coordinates, then include in the draw in the diagram, and you'll get these types of graph. All right. Now let's move on to example 3 with a value for uniformly distributed load here, in order to make you have a better understanding, plus a little extra exercise here, whereby you need to find okay, let's split the question together. The simply supported beam in figure A has the cross-sectional area as shown in figure B. Determine the absolute maximum bending stress in the beam and draw stress distribution over the cross-section at this location. Okay, so question asks you to determine absolute maximum bending stress in the beam. I think maximum bending stress at point B and point D here. All right. Now, the first step is that you need to draw a free body. You need to cut the section and draw its free body diagram. Okay. Remember, for uniformly distributed load here, you need to represent it as an average value for single load. So the distance itself also need to be at the center of the section that have been cut. After that, you need to find reaction force in y direction, and then you need to find its coordinates by substituting the value of x in the equation. Same goes to the moment. Find the value of moment. After that, substitute the value of x into the formula in order to get all the coordinates there. From there, you can draw a shear force and bending moment diagram. Okay. But a little bit exercise for this example. Okay, so maximum value of moment is 22.5 for this case. And from bending moment diagram, L equal to 6 meter, W equals to 5 meter, and from there you can calculate the value of sigma max, which is required by the question. Alright, value of y is given. Moment, yeah, you calculated on your own by using cross-sectional, the cross-section and using the shear force and bending moment diagram. From there, you can locate the maximum value of stress, which represent the maximum value of moment. So if you refer to this formula, which is sigma equals to my over I for beam, maximum moment will lead to a maximum value of stress, and therefore that's why we are always take the maximum value of moment. So for this case, sigma max equals to 12.7 MPa for D point, whereas for B point, location B, y equals to 150 mm. So just substitute the value, you'll get stress at point B is 11.2. So from there, you draw its stress distribution here. Moment moving counterclockwise. So what happened to point B is that it will suffer compression stress, and for point D, it will suffer tension stresses. Okay. Now let's move on to another method, which is using integration to draw shear force and bending moment diagram. Alright. Okay, so this is the relation among load, shear and bending moment. Okay, by taking at this point, you see this is the sign convention as mentioned to you in the previous slide. So remember, different direction of cutting will have different sign convention for internal shear force and also bending moment. Okay. So for this, from this section, cut section, you need to find the total forces in y direction. From there, you'll get this equation, which is dv of dx equals to negative w. By right, dv is actually represent the difference between point D and point C, and integration between point C to D for W towards X direction, or in other words, it is actually represent for area under the curve. It's easy. Alright, same goes to moment. Okay, taking moment at C prime here, then you'll get the equation for moment MD minus MC equals to integration of V dx from point C to point D. Okay, so let's look at this example. I'll show you the simplest way on how to use the integration method by not calculating the integration method directly. Okay, so let's look at this example together. The simply supported steel beam is to carry the distributed and concentrated load as shown. Knowing that the allowable normal stress for the grade of steel to be used is 160 MPa, select the wide flange shape that should be used. Alright, so by right, for wide flange shape, this one is you need to find it using the tables that are going to be distributed to you, or you may find the list itself and the textbook the one that I've been introduced to you before this. So the first step is that you need to draw its free body diagram. After that, as usual, taking moment, you need to find the reaction force at point D and also point A. So you'll get the value of D. Reaction force at D is 58 kilonewton and reaction force at point A is 52 kilonewton. And remember, again, for any question that have uniformly distributed loads in it, and when you want to find the reaction force, other reaction force, for this section, you need to transform it into single load by taking its average towards along the beam, along its load that have been distributed. For this case, 20 times 3, so equals to 60 kilonewton, and it is located in the middle of that section. Okay, only then you may find the value of reaction force at point A and also point D. Otherwise, it is very difficult for us to find those reaction forces. So next is that develop shear diagram and determine maximum bending moment. How to find it is that, okay, for point A, V at this point A, for x equals to 0, we know at this point we have AY. So VA equals to VY, which is equals to 52 kilonewton. So we got one coordinate here, so 52. Now, since this is uniformly distributed, so the graph might have slope in it. So in this case, it will be a linear graph here, and therefore until point B here. So VB minus VA equals to negative 60, equals to negative 60 kilonewton. From there, you'll get the value of VB, which is equals to negative 8 kilonewton. So you'll get another point here, another coordinate here. The first is 52 kilonewton when x equals to 0. So when x equals to 3, you'll get VB equals to negative 8. After that, moving to point C here, you'll get another reaction force here, which is 50 kilonewton moving downwards. And for that reason, negative 8 plus negative 50 kilonewton, you'll get negative 58 kilonewton. Or, and then at point D, you'll get, point D, if you look it back, it is equals to 58 kilonewton moving upwards, so equals to 0 at this point. So this is the shear force and bending moment diagram. However, the question asks you to determine the maximum value of allowable normal stress for the grids to be used is 160 MPa. Select the wide plane shape that should be used. So for this case, the maximum value of moment always exists at V equals to 0. V equals to 0 is somewhere here. So we need to find the value of X here. Alright. How to find the value of X? So we know that this is a linear graph, which is Y equals to mx plus C, right? Okay. So for that case, VB equals to VA here minus WX, the slope itself. So we know that VA equals to 52 kilo minus WX is 20 kilo X. And therefore, from there, you'll get the value of X, which is 2.6 meter. So, for this case, you can either draw a bending moment diagram, or you can determine the bending moment the moment value by taking the value area under the curve for shear stress. Alright, so you know that X equals to 2.6, and therefore you need to calculate the value of area under the curve here for triangle. Then you'll get 67.6 kilonewton. Okay, now if you still remember, section modulus, formula for section modulus equals to moment maximum divided by allowable stress. So that's why we need to find the maximum value of moment. So calculate, substitute the information, the data into the formula. You'll get the value of S is 422.5 times 10 power of 3 mm3. But the question asks you to select the type, to select the types of beam to be used. So by right, you need to refer to the table, the list of tables in the textbook. But here I already summarized it. Okay, so if you refer, please don't look at the answer yet. So from the table, you may find various types of shape with its own value of S. Okay. So the value is different, and the value of S that have been taken from us is that have been calculated is 422.5. So from there, you need to select which is the nearest value for 422.5. Okay. For example, taking a 637, this one, I think this is too far. I guess shape that you might want to consider is 474. This is its shape. And then 448, this is its shape. After that, 535, this is its shape. And 549, this is its shape. So by right, you need to you need to list it down as nearest as possible to the value that have been calculated. So if you refer here to the list here, then the nearest value would be 474 and also 448. All right. However, for this case, we choose this type with the value of S is 474. If we compare to the value of S that have been calculated, it is very far. However, if you refer to the shape, okay, this is the shape and this side is actually its weight. So this one, 32.9 is lighter than 46.1. Therefore, that's why we chose this type of beam. Because you see, in any types of design, weight is also need to be considered, because after all, costing does matter. So the lighter it is, the cheaper it will be. Otherwise, you are going to have higher cost to design the beam. Okay, move on to example 5. For this case, the types of beam is given to you, so you just need to find the value of S in the table, in the list of the table that is going to be given to you, or you may find these types of beam in your textbook at the end of your textbook. Okay. Is simply supported and carries the uniformly distributed load as shown. Draw shear force bending moment diagram for the beam and determine the location and magnitude of the maximum normal stress due to bending. So let's solve these problems together by using integration method. First of all, you need to draw a free body diagram in order to find the reaction force at point A and point C. Okay. From there, okay, you'll get the value of reaction force at point A, 80 kilonewton, and point C, 40 kilonewton. After that, from this point, after that, we need to find the coordinates in order to draw shear force diagram. Alright, so from here, we have a uniformly distributed load until point B, and therefore the equation is VB minus VA equals to negative 20 times this length, which is 6, equals to negative 120. Okay, after that, you'll get the value of VB. Substitute the value of VA. VA is equals to 80 kilonewton from calculation from free body diagram. We'll get VB negative 40 kilonewton. VB. Alright. As for VC, there's no distributed load there, so VC equals to VB, which is equals to negative 40 kilonewton. So this is how you draw a shear force diagram. So 80, starting with 80 kilonewton, moving downwards until point B is equals to negative 40 here, negative 40 kilonewton. And from point B to point C, it is the same, which is negative 40 kilonewton. After that, moving to bending moment diagram. Okay, for bending moment diagram, you need to calculate. Calculate the area under the curve. But before you can calculate the area under the curve, you need to find the value of X there. Okay. Same goes to previous slide. This is how you calculate the value of X. VD minus VA equals to WX. So you'll get VD. You know VD is equals to 0 minus 80. For VA equals to negative 20 times X. So you'll get X. You'll get the value of X is equals to 4. Okay. After that, you need to calculate the area under the curve. Alright. So from there, MD minus MA, you'll get 160 kilonewton meter, and so on and so forth. And you see, from point A to point B is actually a parabolic equation. Alright, this is a graph or shape, parabolic shape, because through integration, if we integrate the linear graph, then it will change to parabolic. Okay, for straight line, when we integrate the straight line, it will become a linear graph, y mx plus c. Okay. So when we want to find the to find the maximum value of moment, it always exists at v equals to 0. So in this case, when v equals to 0, m moment equals to 160 kilonewton meter. So substitute into the formula. This is the formula, maximum normal stress by using section modulus. For a value of section modulus, W, you need to find this shape in the list. After that, you may find the value of S equals to 1280 mm cube. So from there, you'll get maximum stress equals to 125 times 10 power of 6. Alright, MPa. Last example, alright, draw the shear and bending moment diagram for the beam and loading shown. Same steps, you need to draw free body diagram in order to find the value of AY and also D. Okay, you'll get the value of D 115.6 and A 81.2 kilonewton. After that, after that, straight away use the integration method. Okay, at point A, you'll get 81.2 kilonewton from this point, from point A until point B. At point B, you find there's 90 kilonewton downwards. So 81.2 minus 90, you'll get negative 8.8. So at this point, after that, moving to point C here, you'll find 54 kilonewton load acting on C. So negative 8.8 plus negative 54, you'll get the value of negative 62.8. So this one moving to point D. Until point D, you find the value, there's the uniform distributed load there. So for this one, straight away calculate its value, which is I don't remember. Oops. Okay, 22. Okay, 22 times 2.4. Okay, 22. Okay, so you'll get 52.8, and at point E, there's no reaction force, so it is equals to 0. After that, in order to draw a bending moment diagram, you need to find the area under the curve. So 51.2 times 1.8, you'll get positive 1.6.2. And for section BC, negative 8.8 times 2.4, you'll get negative 21.1. And same goes to this one, 62.8 times 3, you'll get 188.4. And this one is rectangular triangle area. Half times 2.4 times 52.8, you'll get 63.3. So by right, if it is straight line, then the graph will have a slope, meaning that it will be a linear graph. Alright, as for this line, then it will change after integration, it will change to parabolic. So this is the graph for bending moment. Please be noted that bending moment at A and E is 0. A and E is 0. Bending moment variation between A, B, C, D is linear. Okay, so linear graph. Bending moment variation between D and E is quadratic or parabolic. Okay, net change in bending moment is equal to areas under shear distribution segment. Okay, so area under the curve is still by calculating the area under the curve, then you'll get the coordinates for moment. total of all bending moment changes across the beam should be 0, otherwise your beam is not stable. Okay, so that is all for the example for today's lecture. I'm sorry because it takes very long time for this topic. However, I hope the example that I've been given to you should be enough for you to understand on this topic. However, if you have any question related to the topics, you may contact me directly in using any types of mediums. Okay. So last but not least, this is the other application involving bending loads. If you look at here, this is wings for airplane. This is what? Okay, this is another example, and this is also is another example. So by right, there are other types of example as well which involve bending load. So whatever it is, the way you calculate is still the same. So that will be all for today's lecture. So see you again tomorrow, I think, with the new topic. And with that, I thank you very much for your kind attention and time. So have a nice day, and bye bye.